I'm assuming that you have been following these lessons and you know how to set your feedback, you know how to look for tip imaging, you have gone through image optimization, you've tried to minimize the number of perturbations on your AFM, but your signal from your photodiode still looks terrible, and it does in your opinion. And this would be when you have your cantilever in contact with a stiff sample, you're not scanning, you've closed up the hood and so forth. And so if this signal is greater than 10 millivolts, I would certainly say that is bad, and you want to be down with a couple of millivolts or 1 millivolt of noise. It's very difficult to guess from a signal that looks like that what might be going wrong in your AFM, and it's much easier to guess if you take that signal and you subject it to a process called a Fourier Transform. And if you do it with a computer, as you likely will, there's an algorithm called a fast Fourier transform that just about everybody uses. What this does is change your signal from voltage as a function of time to frequency as a function of time. And just eyeballing what this might look like, I see a couple of frequencies in that signal, and so the Fourier transform might look something like this: two stronger peaks and some noise. There's also an equivalent process for the reverse. You should know about that. That is called the inverse Fourier transform, or inverse fast Fourier transform. Just to be clear about Fourier transforms, what we have here is a low-frequency sine wave, shown in blue, good amplitude, a smaller amplitude, higher frequency sine wave, shown in rose. There's some shown in purple, and if we take the Fourier transform of this, what we get is one strong peak at what's called the fundamental frequency, the lowest possible frequency that can fit, and then another higher frequency peak. I tried to draw that rose signal at about 5 times the frequency of the fundamental. And so you can see here that the purple signal is simply the sum of two frequencies. This is important because when you're diagnosing noise, it is easier to think about what might be vibrating at what frequency than to look at a time domain signal and figure out what's going on. Let's take a look at some real data. Here are noise spectra of an AFM with what I would call a rigid cantilever. What that means is we're just shining the laser light off the back of a cantilever chip rather than a cantilever. We also turn the laser off and look at the signal from the photodiode then as well. The axes are somewhat different. In the y-axis, it should be a log. It's mean square voltage instead of voltage. Why that? Well, if you take mean square voltage and divide it by an assumed resistance of 50 ohms, voltage squared over resistance, that's power. So sometimes you hear people talking about power spectra as opposed to noise spectra. Either one is fine. On the x-axis, we have frequency. Now it's in kilohertz. Now it's on a log scale. First thing to note is that when the laser is on, there is more noise than when the laser is off. When the laser is on, if you do the calculation, you find that the overall mean square voltage for all frequencies in this range is 2.32 millivolts. With the laser off, it's 1.66 millivolts. So you do want to be down in the millivolt range with your noise levels. Now I want to tell you about some of the characteristics of these spectra. They have all the typical kinds of things happening in noise spectra. And we'll work left to right. So first of all, please note these 2 points here. The slope of those 2 points is -1 on a log scale. Okay? The lovely thing about log-log plots is that if you have data with the slope reveals the power law. So initially, for the laser on situation, with low frequencies, the data are following a 1/f dependence. And this 1/f noise is fairly common in electronics. And you'll see it more evidently in the next slide that I'll show you. Then we have a fairly flat frequency range here. This is the range over which the manufacturer thinks that most measurements will be made. Then here we have some resonances. Resonances happen in electronic circuits just as they do in mechanical components. Then we have a spike. This usually comes from electrical components, and I don't know of such a narrow response in the mechanical component, at least not in air. If we were to extend this frequency range, we'd see a flat response going out. This is called white noise. Okay. White in the sense of all frequencies, like white light is a combination of all the different colors. And oops, I'll add the 0.1 there. By the way, if we wanted to turn this into a log frequency, remember that log of 1 is 0, log of 10 is 1, log of 100 is 2, log of 1000 is 3, and log of 0.1 is -1. You might be curious to see some data of a cantilever now. This cantilever is hanging in the air on the left and immersed in water on the right. We still have frequency on the x-axis, this time just 1 to 100 kilohertz, so a smaller frequency range. And on the y-axis we have log of mean squared amplitude as opposed to log of mean square voltage. So we were able to convert from voltage to nanometers using a calibration technique. Note that in the air signal, it's very clear that we have 1/f noise, as you would expect at lower frequencies. When frequencies are small, the 1/f is bigger. So if we look from 1 to 10 kilohertz, we have a change of 1 here and 1 here. So -1 here, and so this slope is indeed -1, which again, as mentioned before, is 1/f noise. In red here, what we have plotted is the theoretical response of a cantilever, and you see that peak pokes right up at about 20 kilohertz. And the blue dots are the data, and the fits, the black line that you might be able to see in the background, particularly right here, that's the sum of the 1/f noise and our simple harmonic oscillator, which is the model for the cantilever, plus a white noise floor. Now, when we take that cantilever and we put it in water, the same cantilever, note what happens. That frequency is shifted down from 20 kilohertz to 800 or so, and the resonance, i.e. this peak, it's become much broader. Here it's quite narrow, as you see. Okay? That happens because the water dampens the motion of the cantilever. These spectra are important because you can use them to tell you the spring constant of the cantilever. There is a theorem that says 1/2 times Boltzmann's constant times temperature is equal to 1/2 the spring constant times the mean square amplitude over all frequencies. Here we have mean square amplitude for one frequency at a time. Let's list some typical sources of noise along with their typical frequencies from low frequency to high frequency. 1/f noise, that's in your electronics. There's not too much you can do about that unless you're an electronics expert. I do recommend that before you buy an AFM, you ask for the noise spectrum of the tip in contact with the sample without scanning. Next up, the 50 Hz, 60 Hz in power lines. After that, people talking, that's in the few kilohertz range. So if you get that, you need to acoustically shield your AFM. The cantilevers themselves, they run from 5 to 500 kilohertz, typically. These scanners, and the old-fashioned cathode ray tubes, they have a refresh rate of on the order of 20 kilohertz. That resonance you saw 2 slides ago, that's a consequence of electronic filtering. That was at 300 kilohertz. And that very strong spike you saw 2 slides ago is from a frequency generator, such that when you're tuning a cantilever, you need to do a frequency sweep, and that was at about 700 kilohertz. Those are typical numbers for typical things, and you can think of them like a signature, just as that's my signature, and they will give you a clue as to what the cause of noise in your AFM might be.